So now we are ready to talk about the classifiers. Okay, so one is called quadratic discriminant analysis. The short notation is just QDA. QDA. Suppose we only have two classes. Two classes. So one class is we denote by C. For example, cancer group. Okay, another class we call it D. No cancer. Okay, and the base classifier is R star X equals to C. We predict the classifier based on the feature X value. We predict C if the Q function of the class C given this X is greater than the Q function, the value of the Q function at other class D. Okay, otherwise we predict the class D. So in other words, we pick the class with the biggest posterior probabilities. Recall, since this Q function is quadratic, and we call this gives us a quadratic decision boundary. This gives us quadratic decision boundary. Which is QCX minus QDX equals to 0. Okay, so for example, for D equals to 1, maybe we just pick, for example, the QC is a function here, QD is a function here. Okay, QC is here, QD is here. Okay, we have two functions, and the decision boundary is just a point. So this is a decision boundary. Okay, for a two-dimensional case, we have two-dimensional counterplot, and this, for example, here we just have the decision function as a quadratic function, Okay, so this is a decision boundary. And the QDA is that you can estimate the probability your prediction is correct. So the advantage of the QDA. We can obtain the probability your prediction is correct. Probability prediction is correct. that your prediction is correct. So what's and this is something that support vector machine cannot do. Maybe let's work out how to quantify this probability. Okay, actually, do you remember based on our last lecture derivation, the posterior distribution given the x data x, you observe this class C. This equals to, this is the posterior, right? This is the posterior. Equals to the probability of the px, right? Numerator is the prior probability, x given y equal to C, and times the prior probability class C. And this equals to, because we have the full total probability rule, we can calculate x given y equal to C times pi C plus probability x given y equals to D, another class, pi D. The numerator is same, x given y equal to C pi C. This is called the Bayes rule, Bayes theorem. And recall, remember we want to present this as using the Q function. So recall e to the power q x equals to what's the QC? QC is the natural log of this quantity, right? If you take the exponential, you will get f x given y equal to c x times pi c. And actually this will simplify to e to the power qc x divided by e to the power qc x plus e to the power q dx. And then we can divide the quantity top and bottom, e to the power qcx. We can divide e to the power qcx. We divide the numerator and denominator same time by a constant. We can get 1 plus exponential qd minus qc, qdx minus qcx. Recall this is nothing but just our decision function, right? This is a decision function. Okay, so and in summary, we rewrite our posterior probability is equals to 1 over 1 plus e to the power some quadratic function x minus q c x. Okay, actually this is just can be written as a function of the s q dx minus q cx, and this s is a function will be famous, very, very popular. You're gonna see such function a lot. This equals to the 1 plus e to the power t. Power negative t, sorry, negative t. Negative t. Negative t. This function has a special name called logistic function. Or in the neural network, it's called a sigmoid function. In deep learning. Okay. So actually, for the logistic function, you can plot this function on along the x-axis. So this function will have the S shape. So it's okay. So it when the t equals to 0, when t equals to 0, this equals to 0.5. Okay. So in other words, this function has a property when the value is 0 equals to the 50% chance, so 0.5. Okay, and the limit of this function when t goes to infinity, st, it will goes to 1. This is 1, and this, so this will goes to 1. And when limit when t goes to negative infinity, so goes to this direction, your logistic function will goes to 0. So this s equal to 0 means what? This means on the decision boundary there is a 50% chance our observation will belong to class C. Okay, so this means 50% chance probability. To pick C or D. Okay. Actually, this by deriving this will give us the this works for the multi-dimensional case, multi-class case too. So, for example, we do you remember the first class to classify handwritten digits? To 0, 1, up to 9, right? We have, in that case, we have the 10 classes. If that's the case, we will have this quadratic decision boundary. We'll have quadratic decision boundary. You typically wind up with multiple decision boundaries that adjoin each other at joins. It looks like a sort of the Voronoi diagram. It's a special kind of actually it's called multiplicatively weighted Voronoi program. This is called additively weighted Voronoi diagram. Okay, for example, if our observation falls into this region, we pick a number 1. In this region, we pick number 1, we pick number 1. And in this, we pick number 2, pick number 3, pick number 8, something like that. Okay. Oh no, sorry. So each class we have a unique number. So 1, 2, 3, maybe this is 4. This is 7, this is 9, this is 0, something like that. So it can be used for predicting the, so this quantity shows us this after this quantity shows us the posterior probability we are making the correct decision.